On behalf of the Royal Statistical Society, I would like to welcome you all to the 5th discussion meeting of 2025. For those ones that don't know me, my name is Ruth Vieira. I am a senior lecturer at the University of Aberdeen, and I am also the chair of the Royal Statistical Society Medical Section, who is sponsoring this event, so that's why I'm here. So we will be discussing today the paper Balanced and Robust Randomized Treatment Assignments, the Finite Selection Model for the Health Insurance Experiment and Beyond by Chattopadhyay et al. So the meeting here at Hallam Conference Center for the Royal Statistical Society also welcomes an online audience. Please keep the microphones muted and the cameras turned off throughout the meetings unless we ask you to turn them on. A recording of the meeting will be posted on the RSS YouTube channel. If anyone prefers not to be filmed, let us know and we can edit that part out. We are looking forward to hearing the discussion a little later, and we have some who already booked slots in advance. But if you would like to comment and have not booked, we will open the floor up to discussion near the end of the session if time permits. Additionally, we actively encourage you to contribute in writing by a deadline of 19th of November. All comments can be written up afterwards, around 400 words, and they will be published in the journal Series A along with the paper. So do we have any questions on the floor or online before we proceed? No questions? Okay, so the paper will be presented by authors José Zubizarreta, visiting from Harvard University, and Ambarish Chattopadhyay, visiting from Stanford University. And it will publish in the Journal of the Royal Statistical Society Series A in 2026. So I would like now to call on José to open the presentation.
Thank you very much, Ruth, for that kind introduction. I would like to start thanking the Royal Statistical Society for having us here today. It's a very big honor for Ambarish and I to be here today, sharing our work, and also honoring and remembering the life and contributions of our co-author and mentor, Professor Carl Morris, who passed away during the final stages of this project. So thank you so much. The question that motivates this work is how to estimate the causal effect of a medical treatment or a policy intervention. As we know, the ideal way of doing this is by running a randomized experiment, which is representative of a population, where there's no compliance, no differential attrition, and so on and so forth. So the answer is an experiment. But more specifically, the question that motivates us is how to design these experiments as efficiently as possible, namely, how to make better use of the ever-scarce resources available for experimentation in such a way that we spend less money for that level of statistical power, or in terms of lives, how we expose fewer patients to a treatment that is potentially harmful to the patients. As the title of this talk foreshadows, one answer to this question is the FSM. To us, the FSM is a hidden gem of the literature in causal inference, so to speak, maybe well known in other literatures, but not to us. So to tell you a bit how we come to learn about this gem, I'd like to tell you a little story. This maps back to the fall of 2017, when we were having lunch in the healthcare policy department, which is an interdisciplinary department at Harvard, formed by economists, doctors, and statisticians like myself. We were having lunch with Professor Joe Newhouse, Professor Suri Song, and Jay-Z, that's me. And while having lunch, Suri was working on an experiment where he had 3 treatment arms, and he wanted to randomly assign subjects to these treatments, but achieve good balance. He was asking us, okay, what should I do? And I thought to myself, well, blocking is one alternative, but blocking suffers from this course of dimensionality. We can block for so many variables only. Second, I thought about mixed integer programming. You know that if you have a hammer, every problem looks like a nail. But then inference is not straightforward. And of course, rerandomization, which is widely used nowadays, especially in the social sciences, in development economics. But the balance that it achieves can be brittle in the sense that it doesn't target a very large function class for the outcome model and has tuning parameters that require some thinking, we think. And then there's the added question of what happens if you have multiple treatment arms, not 3, maybe 13, as it happens in the experiment that we're going to describe a bit later. What do we do in those settings? So I was a bit puzzled. But my colleague and mentor, Joe Newhouse, smiled. He said, use the FSM. The FS what? I thought. I should know about that. I work in causal inference. And he told me that this was a method developed by Carl Morris back in the 70s when developing the health insurance experiment. So it was time to call Carl. Carl Morris, as you know, was a towering figure in statistics who made many contributions, including empirical Bayes, hierarchical models, and shrinkage. To me, he was Mr. Mathematical Statistics, so I didn't know about this area of his work, which is more applicable, as Professor Brad Efron would say. Not applied, but applicable, okay? And I was very amazed to know about this aspect of his work, and moreover, that he had the time of his life working on the FSM back at RAND for the health insurance experiment. So it was really wonderful to start learning and working with him, revisiting and extending the FSM. Very lucky to us with the great work of Ambaresh Chattopadhyay, at the time a PhD student at Harvard. So we started working on this. The FSM was developed by Carl in the 70s for the design of the famous health insurance experiment, which was this massive experiment in the domain of health services research and more broadly the social sciences, where they randomized about 3,000 families to 13 treatment arms in many locations to understand the elasticity and the willingness of families to pay for more healthcare and how much they actually use it according to how much they pay. Very critical questions then and also today in the US and I would say in other countries too. So they ran this experiment for this very important policy question, and as it happens when you go to the moon, other things happen, other things get invented. So what got invented here was the FSM by Carl, which I think is a very clever method that we are revisiting, formalizing, and extending in this paper as a general tool for experimental design. So in this paper, what we do is to describe the FSM using the potential outcome framework for causal inference, extended by proposing a new optimality criterion for the FSM inspired by the criterion of D-optimality in experimental design. We demonstrate that it retrieves several classical designs from the experimental design literature, such as stratified, blocked, and paired experiments, and also extended to stratified and sequential settings. And we also illustrate its performance. In a nutshell, as a preview, Ambaresh is going to tell you a lot more about this. The results can be summarized in this figure here, where we're comparing the balance that complete randomization, rerandomization, and the FSM achieves on main covariates and second-order transformations. Here we're giving a bit of an edge to rerandomization because we're asking rerandomization to balance the second-order terms and FSM only the first-order terms. And we can see that it achieves between 68 and 56 better covariate balance than complete randomization and rerandomization respectively, across 10 studies that we revisited from the literature in development economics. And in turn, better balance translates into a more efficient design at the end of the day. And Amber is just going to tell you more about all this. Thank you so much for having us.
All right. Thank you so much, Jose. Thank you, everyone, for being here. Can you hear me clearly? All right, good. So now, after all this introduction, how does FSM work? What is the FSM thing, right? So Jose took you back to 2017. I'll take you back to even further, to our own childhood days. So I'm pretty sure when we were all kids, we have played games like this where, you know, there are two teams with two captains on the left and a bunch of players on the right. And the captains used to take turns in choosing the players for their own team. Right? So for example, this girl is like, I choose you. And the other girl, this guy is like, I choose you. So in this way, they take turns and build their own team, right? Now, obviously, you are trying to win a game. So obviously, at every stage, you are trying to choose the best player that you can get, right? Now, suppose both these captains have the same idea of who is a good player and who is a bad player. So they have the same knowledge of players' strengths, okay? So at the end of the day, what would you expect? The two teams would be pretty similar, right? Because they're choosing based on the same idea of players' strengths. Now, suppose their idea of player strengths are actually very correct. So they are correctly knowledgeable of player strengths. So the player that they think is good is actually good. So then not only they will be similar, they will also be pretty strong, isn't it? Now the funny thing is, suppose they're completely wrong about player strengths. So let's say this guy thinks that this player plays football like Messi, but in reality he plays football like Ambrish, which is very bad. But even if they're wrong, they're equally wrong. So at the end of the day, the two teams will still be similar, right? So this is the idea of the FSM. Why? Now you simply replace the captains by treatments and the players by units, individuals. And you get this whole idea of FSM. So in the FSM, instead of units being assigned to treatment groups, here treatments are choosing units for their own group. That is the main difference between FSM and the other designs. And by cleverly deciding the order of selection and by what criteria they select, you can ensure that your treatment groups would be well-balanced, efficient, and robust. Okay, so this is the basic idea of the FSM. And now notice that there is nothing special about two teams. You can have 17 teams, and the same idea applies. They will take turns in a certain way, and then they'll choose players for their own team. So this thing works for multiple treatment groups. It seamlessly extends to multiple groups. So with the FSM, formally speaking, we'll try to develop a method that assigns n individuals or n units to G groups. G can be more than 2, G can be at least 2, of prefixed sizes, n1, n2, ng. Okay? That's the idea. Now, obviously, many questions are appearing. First of all, one question is, in what order should they choose? Who should go first? Who should go second? What is the order, right? And the other question is, once you know the order, let's say treatment 1 chooses first, or team 1 chooses first, who to choose? Who's the best player? How do I know who's the best player? So what is the criteria that should be used to choose the players? This is answered by two main components of the FSM, which Carl used to call, the first component Carl used to call selection order matrix, and the second one, the criterion, is called selection function. And I'm going to go over each of them separately now. So let's start with the order. What is the order of selection? Okay, just as an example, let's say we have 12 units, and we want to divide them into two groups of equal size. So 6 each, we want to divide them. One possible order of selection is like this. So I have 12 stages of selection, and on the right, the second column, you have the label of the group that selects. So it says that the first 6 choices are made by treatment 1 or team 1, and the next 6 are made by treatment 2 or team 2. That's one possible selection order, fine. Now, I don't know about you, but in the game context, I would not want to watch this game. Because team 1 will completely thrash team 2. It's getting all the best players beforehand. You're being unfair to team 2, right? That's not a good selection order. So selection order should be fair. It's being unfair, so we don't want that. And also it should be random. we want to have a randomized design, right? So because we want to balance these unobserved covariates that Jose was alluding to, and also we want to do inference. Randomization gives us a natural way to do inference. So we want it to be fair and we want it to be random. Okay, how do we do that? Well, one possibility is this. What we do is we divide the successive pairs of stages, like this, using the dashed lines here. Now within each pair, we flip a coin to decide who goes first. So in the first pair, notice, I flip a coin and I say that, okay, treatment 2 goes first, and then treatment 1. In the next pair, independently, I flip a coin again, and I decide, okay, treatment 1 goes first, and then treatment 2. In this way, notice it's random, because I'm randomizing for each pair. And it's also fair because no one is really getting the upper hand. We'll never have a scenario where we'll have 1, 1, 1, 1, 1, and then 2, 2, 2, 2. It will not happen. Okay? So this is one way to do it for equal-sized groups. How about unequal-sized groups? Is there a way to generalize this? Yes. So one way to notice that this way of generating this order has a nice property. And this property is formally called sequential control. So what is it? Let's explain. So SR is the number of choices made by treatment 1 up to stage R. How many selections it has made. And FR is the expectation, right? So in this context, FR would be R over 2, right? Because there are equal-sized groups. Sequentially controlled means that the difference, the absolute difference between SR and FR is strictly less than 1. What does that mean? It means that the number of choices that treatment 1 makes doesn't depart too much from its fair share, right? So this is sort of the condition for fairness that we impose on the design. Now, this works for the equal-sized group. For unequal-sized group, it turns out there is an algorithm that can ensure that you will have this sequential control. And this is the algorithm that I wrote here. I don't want to go into too much detail, but essentially, if you follow this, you will show that this satisfies the sequential control condition. Okay. Not only that, this is a unique Markovian sampling algorithm that is sequentially controlled. What do I mean by that? It's Markovian because, I don't know if I can move the cursor. So, okay, because the selection that I make in stage R plus 1, if you look at the second bullet point, depends on the choices made up to stage R. That's why it's Markovian. And it's sequentially controlled because it satisfies that sequential control condition. Okay? So it's a unique Markovian sampling algorithm that is sequentially controlled. Now, you said, okay, Ambarish, this is good for 2 groups. How about multiple treatment groups? Can we do that? Yes, in some cases we can do that. So in the paper, we extend this idea to multiple treatment groups, where obviously we have to extend the notion of sequential control. And how do we do that? Now, instead of defining SR and FR, we have to define it for each treatment group. So for treatment group G, we define this sequential control condition, and we develop algorithms that satisfy this property. So we are kind of done with the order of selection. So now we know after this how to generate the order in which the teams or the treatments will select units. Okay? Now the next question is, now that I know the order, what is the criterion? How do I know who is the best player? What's the criterion that decides who the best player is? So let's talk about that now. Here is the first time that the notion of potential outcomes will come into play. So suppose treatment 1 gets to choose at stage R. And suppose for now that we assume a form of linear model of this potential outcome Y1. Y1 is the outcome that you observe if you're in treatment 1 group. So we are assuming a linear model like this where X's mean the covariates, epsilon is the error term, the usual stuff. And we know that if you estimate the coefficient beta by ordinary least squares, the variance of that is sigma squared X transpose X inverse, where this X tilde thing is the design matrix. And the generalized variance, one way to summarize this whole variance matrix is by the generalized variance. That's the determinant of it. And in optimal design, the notion of D-optimality says that you want to minimize the generalized variance. A D-optimal design minimizes the generalized variance. So in effect, it maximizes the determinant because it's inversely related, right? This is the idea that we use to figure out our criterion. How do we do that? We try to maximize this D-optimality sequentially. So let me show you. So suppose we are choosing, right? At every stage, every treatment group is making a selection. And let's say the script R minus 1 is the set of units that you have not yet selected after stage R minus 1. And now treatment 1 is selecting. So this is the current design matrix in treatment 1. If unit I is selected. So X tilde Ri, R denotes the stage and I denotes the unit that would give you the new design matrix if that unit is selected. So X tilde Ri is the design matrix in treatment 1 if unit I is selected. And we do this for every single I in this unselected set. And we choose that one, the one that maximizes the resulting determinant. So that's the third line. Choose unit I prime that maximizes the resulting determinant of the X transpose X matrix. So we are trying to go to towards that D-optimality, but not directly, in a sequential manner. And this is the way the sequence is determined. Okay, so I first told you the way to select the order. The next was the selection criterion. And this is the D-optimal selection function, or the D-optimal selection criterion. Okay? Now, why D-optimality? Why not something else? There are so many letters in the alphabet, A, G, E. Why D? Because it has some nice properties, and that's what I'm going to talk about now. The first thing that we get, this is a very messy theorem, but essentially what it says, it connects this selection to the notion of Mahalanobis distance. It says that, okay, this D-optimal function chooses unit I prime such that it maximizes this type of a Mahalanobis distance. Okay, so let me explain what's really going on here. There is a mean X star R minus 1. At the very beginning, when any treatment group has not selected anybody, it tries to choose something that is farthest from the overall sample mean, right? And at the later stages, it tries to choose a unit that is farthest from its current mean. So you see what's happening at every stage, you're trying to increase the dispersion of your own group. You're trying to increase the information available in your own group. And we know that efficiency is directly related to information. The more information you have, the more spread out your X's are within your own group, the more efficient would be your regression coefficients, the estimated regression coefficients. So every single time, every treatment group is trying to choose a unit that is farthest from its current mean. And that's why they're increasing the spread. Okay? So this is sort of the direct connection to Mahalanobis distance. What does it buy us? It buys us many things. One of them is that this selection process is affine invariant. So it's invariant to any affine transformations of the X's. What does that help us? So if you measure your weights in kilos versus pounds, doesn't matter. It will make the same choices. And that's what it should happen, right? It shouldn't change any decision based on the unit of measurement. So that's a good thing to have affine invariance. All right. Another thing that we get is that if your data is symmetric, then you can show that by doing this exercise, you can get exact balance on even functions of the covariates. So let's say the covariates are centered, they have mean 0. That means that if your data is perfectly symmetric, you get exact balance on, say, the second order moment or the fourth order moments and so on. That's another nice property to have. And notice that here I don't really have any tuning parameter. In practice, the tuning parameters are hard to choose. But here I don't have to go through that trouble, so I'm all set. And the fourth thing that is very interesting is that by doing this sequential and random exercise, we end up getting something that has been there in the literature for many, many years. As Jose was saying, like we get randomized block design, we get matched pair design. So how do we get that? So just as an example, let's focus on the randomized block design part. Let's say we have B blocks and G treatment groups. In your FSM, if you just include an intercept and the indicators of the blocks, you automatically get an assignment that you would have gotten by doing a randomized block design. So you don't have to separately randomize within each block. Just run the FSM. You get something exactly equivalent to RBD, randomized block design. Similarly, if you have identical twins in your data, right, then ideally what you should do is you should do a matched pair design. You should create these pairs and then randomize within each pairs. FSM is saying, no need to worry. Just run the FSM using a model like this, intercept and X's. It will automatically do what a matched pair design does. Now this saves a lot of computational cost because say in your data set, there are some very close twins, but you don't know. So here you don't have to worry, you just run the FSM and you get a matched pair. Otherwise, you have to first identify the pairs first. That's a lot of work. Here it doesn't, you don't have to do that. So it automatically retrieves these classical designs. So that's why D-optimality turned out to be a very nice thing as a selection criterion. Now you'll say, okay, Ambarish, so far so good, but does this thing actually work? Jose was saying that one of our criterion in the paper was to actually evaluate the performance of the FSM, whether it works in real experiments or not. So let's try to see that, but let's not start with the real experiment right away. Let's start with the simulated experiment. So I have a simulated data of 120 individuals, and I want to divide them into 2 groups of equal size, okay? And I have 6 covariates. The 3s are, you can see all of them. The first 3 are drawn from a multivariate normal. The 4th one is drawn from uniform. 5th one from chi-squared. And the 6th one is a binary one, a Bernoulli one. Okay, so I have these 6 covariates, and I want to balance them. So I'm going to compare the FSM with complete randomization and re-randomization. What is re-randomization? Just to freshen up our mind, re-randomization is essentially you randomize, you check if balance is good or not, balance is good enough. If it's good, you keep it. If it's not, you throw it away and do it again. That's why you re-randomize. And the balancing criteria is based on the Mahalanobis distance. That's the one that we use here. You can use other balancing criterions as well. And this is what we see. So what's going on here? What we compute here is this thing called the ASMD at the bottom. What is ASMD? We have 2 groups. For any variable u, the ASMD is the measure of how imbalanced or how different the mean of u is across the 2 groups. So u1 bar and u2 bar are the mean in treatment group 1, treatment group 2, right? And it's standardized accordingly by their variances. So I want this to be small. So if this is 0, that means their means are exactly balanced. If they are small, I want them to be small at the end of the story. And what I'm plotting here is the distribution of this ASMDs across all these covariates and across different randomizations. And I have, you can see the legend over there, I have CRD, complete randomized design, re-randomization 0.01, so that means it accepts 1% of randomizations. RR 0.001, it's more stricter, and the FSM. So now if you notice, the FSM here it's slightly better than RR 0.001, but not too much better. If you look at the corner over there, the average ASMD under FSM is 0.031, for RR is 0.034. So it's okay, it's fine. But I would say that it's expected, because re-randomization is actually trying to balance the means in the way we have defined it. So let's see actually how it balances the other functions that it didn't include in its criteria. So for this, we look at the next figure. Here we are plotting the ASMDs of squares and interactions of the covariates. These are very important. In many cases, not just the main covariates, but their interactions are also very important. So we need to sort of check balance on these functions, whether they are balanced or not. And here we see a striking difference. If you look at the numbers over there, RR 0.001 has an average ASMD of 0.127, and FSM has 0.037. So we are gaining a lot by doing the FSM, by balancing these functions. So it is behaving more robustly compared to re-randomization. Okay, now a third plot that I'll show, it's on the same line actually. So here I'm plotting the distribution of the difference between the correlation matrices of the covariates. So the lower the values are, the better. So these are the box plots. And notice that the FSM1 is down at the bottom. The right one is all the way down. In fact, it looks like the worst possible value of this thing under the FSM is better than the best possible value of the others, right? So the moral of the story essentially is that it is balancing not only the main covariates, the linear terms, but also the squares and interactions, the correlations very, very well. And that was a very sort of satisfactory thing to see, that with FSM we can achieve that kind of balance. But this was based on a simulated data. How about the HIE data that Jose was talking about? So in this paper, we kind of considered a version of the HIE data based on this paper, Arundine et al., where we have 4 treatment groups, and we have like 1,887 odd families, and we have 20 covariates, okay? And I have a similar plot for all this here. I have the plot for the main covariates, I have plot for the squares and interactions, and the third is the Frobenius norm, the box plot that I just showed you. The same plots for the HIE. Notice similar things here. FSM is doing pretty good on the squares and pairwise products and the Frobenius norm, but not only that, it is doing very good on the main covariates as well. If you look at the numbers, rerandomization has an average ASMD of 0.042, and FSM has an average ASMD of 0.011. So even on the main covariates, which rerandomization is supposed to balance really well, FSM is doing a lot better. Why is that? We'll see. We'll try to answer that at the very end. But looks like balance is, in terms of balance, FSM is doing pretty well. And as Jose was saying, balance translates into efficiency. So we'll see that now. How does it work in terms of standard errors? So here, what we are looking at is an average treatment effect of treatment level 3 versus treatment level 2. So SATE means sample average treatment effect of 3 versus 2. And I have these two potential outcome models that I consider. So in the first model, model B1, the outcome is linear on the x's. You can see very clearly. And then in the second one, the outcome is linear on the x and the x's and then some of the interactions. You see x2, x3, x4, x5. These are what we mean by the interaction, the product terms. And for the sake of comparison, we just assume that y3 is same as y2. So the effect, the treatment effect is actually 0 for everybody. That's the truth we are assuming. And these are the two models. And this is what we see. What I'm tabulating here are the standard errors relative to the FSM. So for FSM, if you look at the columns corresponding to the FSM, it's always 1 because I'm dividing it by the standard error of the FSM. So anything bigger than 1 would show that it has higher standard error, right? And we are seeing that both CRD and re-randomization, they have a higher standard error, both under model 1 and under model 2. Okay, so even if the model is linear in the axis, which is model B1, FSM is much more efficient than the other two designs. Same thing happens with model 2. And this is for the HIE data. So in terms of efficiency, balance, we see that there is a direct translation of balance into efficiency. Okay? All right, how about computation? So in the comparison that we ran, one assignment took 78 seconds with re-randomization on an average, and 28 seconds with the FSM. So it seems like it's also doing a faster calculation. Okay, so that was the whole story with the HIE data. And as Jose pointed out, we also ran all these comparisons based on 10 important case studies, randomized studies in social sciences. You can see all these studies. And we kind of see very similar patterns. So I'm going to show you this big picture that is very hard to see. So let's not bother even going through it, but I just wanted to show that all these comparisons are there. But if you squint your eyes really hard, you'll see that the same result holds across all the studies. So just to highlight, I'm just going to give you a snapshot of the results. So here I have picked up 6 of them that has really high number of units. You can see there. And the covariates are also pretty large, 20, 34, and so on. And what I'm tabulating here is, again, the ASMDs for the main covariates and the second order covariates. If you focus on the columns in red, you can notice that almost for all of them, FSM has the lowest value, and it is lower by a big margin pretty much. The same story holds for second order terms. Okay? So across all these designs, across all these studies, we are seeing that FSM does really good balance on both the main covariates and the second order terms. So what's really going on? Why is FSM doing so much better? So let's try to give you a basic intuition on this. You have to realize the reason why I chose all these studies is because the n's are large and so the possible space of assignment, all possible randomizations is really vast. And so just as an example, if you have n people and you want to choose nt people, the total number of choices is n choose nt. If n is very large, this would be huge space of possible assignments. Some are good, some are bad. What re-randomization does is re-randomization says, okay, these are my good assignments. It chooses a feasible set. And it tries to choose assignments until you land in that set of good assignments. So it tries to get rid of the bad assignments first to end up having a good assignment. So in a way, re-randomization is doing, algorithmically, it's doing a resampling type of exercise. And it's solving a feasibility problem. The set of good assignments, that's the feasible set. As long as you are outside the feasible set, you keep drawing, and at the end, you land in the feasible set and you're satisfied, right? Now, because the set of assignments is so vast, the feasible set, if you want to get really good balance, you have to shrink the feasible set. And landing in the feasible set becomes really, really difficult. It can take a long, long time so that you land in the feasible set. But if your feasible set is bigger, you may land quicker, but you may not have enough balance. That's what we are seeing in the data set. So technically speaking, you could have made the feasible set really smaller. You could have made the re-randomization threshold much more stringent. You could have improved balance on re-randomization, but that would have taken even longer. But is it guaranteed that that would even be better than the FSM? So for that, we'll see an exercise, but just to point out one crucial difference here, that FSM is not doing that. FSM is not solving a feasibility problem. It is directly trying to reach to that D-optimal design in a sequential way. So it's not trying to find out the bad assignments and throwing them. It's directly trying to get through those space of bad assignments to the good assignments directly. So it cuts through the space more effectively, more efficiently. Okay, so to see this whole thing work out, what we did is, so re-randomization here is based on this Mahalanobis distance criterion. So we generated many assignments of the Mahalanobis distance. So we ran kind of like this whole thing for 100 hours, and we generated over 10 million random assignments. And this is sort of the distribution of the Mahalanobis distance that we got. So on this table, I have 3 rows. On the first row, I have complete randomized design. On the second row, re-randomization with 0.01 tolerance. And on the third row, we have the FSM. Now, if you notice, for the FSM, look at the maximum value. That's 10.6. So that says this is the worst possible value of the Mahalanobis distance that you can get in this 10 million random, based on these 10 million random assignments. And for complete randomized design, if you look at the minimum value, that's 18.5. So the worst possible value of the Mahalanobis distance under the FSM is still better than the best possible value under complete randomized design as well as re-randomization. And this is happening because FSM is trying to get to the good assignment sequentially. So it's cutting through the space of all these bad assignments more effectively, right? So what does the implication of this is? That if you run re-randomization and get one re-randomization output for like 100 hours and you get one re-randomization, you are not guaranteed to have something better than the FSM. So it seems, from this at least, it seems like it's a very powerful tool for experimental design because it gives you such good balance and such quickly. Because notice, this took 100 hours, but for generating one FSM, you just take 30 seconds. So for 30 seconds, you're getting something better than what you would have gotten if you ran this thing for 100 hours. So that was very reassuring for us. All right, so this was the story about the FSM. There could be many extensions of this work, and which we are thinking about now. Extensions such as in stratified experiments. So in many experiments, you have predefined stratas, and you have defined sizes, treatment group sizes within the strata. How do you run FSM on that? Can you do that? Yes, we can do that. The whole idea is you have to change the order of selection in such a way that the stratum size conditions are met. That's the only thing you have to do, and there are versions that we have proposed in the paper. The second one, a very important one I would say, is sequential experiments. In many cases, patients arrive to doctor's clinic in batches, in groups. You don't get the patient data all at once. Let's say on the first day, like 20 patients arrive, the next day 10 patients arrive. So they arrive in batches. Can we assign them to different groups using the FSM? Yes, we can. So in the sequential experiments, what we do is we essentially aggregate the information from previous batches. So we create an X design matrix based on the previous batches. And based on that, we try to evaluate the assignment for the next batches. So we continue the information from previous batches to the next batches. That's what we call a batched FSM or a sequential FSM. Okay? So we can extend the FSM to stratified and sequential experiments. And if you have an experiment at hand and you want to run the FSM, how to do that is very easy because it's available on CRAN. There is an R package on that, and instructions or step-by-step, detailed instructions on how to run the FSM is also available on this accompanying paper. Well, we have like examples and vignettes, so it's very easy to follow. And that's more or less it. So I'll end by saying that over what we had tried to sort of convince that FSM seems to be a very good general tool for experimental design. It's very practical. It's very simple. You saw the idea. It's basically taking turns and selecting players. And it's very efficient, and it's computationally also pretty fast. So it looks like it could be a good design for, in general, across fields. So let me stop here. Thank you again so much for being here and for giving this opportunity. We also want to acknowledge Alfred P. Sloan Foundation for their support on this work. Thank you again. Thanks so much.
So thank you very much, Jose and Ambarish. We will now move to the proposers, and I would like to call on the first proposer, which is Stephen Gilmore from King's College London.
I would like to start with an apology to Jose for spelling his name wrong on my slide. I noticed that too late. But I'd really like to start by congratulating the authors on the paper, a thought-provoking paper. And the comments I have reflect my background. So I work in the design of experiments, maybe more mainstream design of experiments, theory, methodology, and applications, more traditional applications, agriculture, industry, pharmaceuticals, various biological experiments. Very rarely in social sciences, and I think never or almost never in public policy. So I was sort of trying to relate the methods in the paper and the problems in the paper to what we would do as traditional experimental designers. So some things I particularly like about the paper and the methods developed in the paper is just the emphasis on good design and its necessity for causal conclusions to be drawn in things like public policy experiments. I think there's quite an increase in the use of experimental methods in these sorts of areas, and it's really important that design gets its proper place in that work. I also like the emphasis on the importance of randomization. As I said, it sort of tries to make social science a science, or to be even less polite, it's the only thing that raises us above the level of the beasts. So I think randomization is really the foundation of causal inference. Another thing I liked, which didn't really come out in the presentation very much, was the balanced view between model-based inference and design-based inference. And I very strongly believe that those who are primarily doing model-based inference should absolutely pay attention to the design and the way the experiment was randomized. And likewise, those who are doing design-based inference don't have to be straitjacketed into doing nothing else. They can introduce other elements into their model. I also found the additional examples a really great source of inspiration for further explorations, and I hope lots of other people will do so as well. So in the time I have, I want to say a bit about how does traditional design of experiments fit into this, or how could it perhaps fit in different ways. So when I teach design, this is the way I say start thinking about planning an experiment. You start off with the objectives. Why are we doing the experiment? What are we trying to find out? And that should lead you to a choice of treatments, the interventions which are going to be compared, or in complex cases, there may be a candidate set of treatments which need further choice. And you need to think about the structure of these treatments. Are they multi-factor, multiple factors? Are there levels of continuous variables and so on? Separately from that, we think about the experimental units, so the things to which the treatments are applied. We have to identify what they're going to be in the experiment and think about any expected patterns of response which we would expect to see in these, which we can use to define the unit structure, things like blocking or multi-way blocking, row-column designs, and so on. So in the HEI experiment, the treatments are the 13 different insurance types of insurance, and the units are the families, I think. The third one here doesn't really apply in this experiment, but sometimes some particular treatments have some particular groups of units have to receive the same treatment or the same level of some treatment factors. And then given all that, we choose a suitable systematic design, perhaps an optimal design. It's usually optimal in some way, even if you don't describe it that way. And then finally, we randomize that systematic design in accordance with the unit structure. So either completely randomize it or randomize it within blocks or something more complicated. Now, I was interested in the comparison between the finite selection method and blocking. So this was mentioned in the paper, blocking was mentioned in the paper, but not really pursued very much. So finite selection model tries to balance treatment allocation with respect to the baseline covariates, which can be continuous or discrete, binary or multi-level categorical. And they try to, but what does balance actually mean? So what type of imbalances do we have to avoid? And I found this a little bit, in the paper it said allocations have to be fair to all the treatments, but what does fair actually mean? And I know there's this measure of sort of the comparison of the centrality of the two or more treatment groups, which is one way of doing it, but is that really what you need? If instead we use blocking in the traditional sense, it's clear. What we want to do is we want to ensure that the variance between units in the same block is much smaller than the variance between units in different blocks. And this method of allocation, SCOMARS, I think is with D-optimality, gives something that at first glance looks like a randomized complete block design or perhaps an extended randomized complete block design, but it's not actually used as such. And I'll come back to blocking shortly. But this is the same table which the authors showed in their slide presentation, or based on the same table, where there are the artificial example, where there are small artificial example, where there are 12 units, and they're randomized in pairs. So first of all, 1 and 2 are allocated to stages 1 and 2 at random, then 1 and 2 are allocated to stages 3 and 4 at random. So that looks a bit like a block design with blocks of size, a complete block design with 2 treatments and blocks of size 2. But it's not, because if you look at the first 2, in terms of in this case, only covariate age, they're at opposite extremes. One takes the smallest stage, one takes the largest stage. So they're not creating a block in the normal sense. But actually, it's interesting, if just down to the vagaries of the data set, if the second most extreme point had been on the low side rather than the high side, then you would have got 2 very similar ages in stages 1 and 2, probably 2 very similar ages in stages 3 and 4, and so on. The way it works out here, you tend to have opposite ages in the different stages. So the choice of optimal design points is very different from the usual, at first glance at least, very different from the usual optimal design. So if I was thinking about it, I want to choose a design which is DS optimal for estimating the treatment parameters, allowing for the covariate parameters. What's done here, if we ignore the sequential aspect and take the global method, which is briefly mentioned in the paper, I think is actually DS optimality for estimating the covariate parameters optimally, allowing for the treatment parameters, which seems like the wrong way around. Now, proposition A5 shows that this does give D-optimal designs for 2 treatments, but I don't think in general it does for more than 2. Perhaps it does if you fix the treatment allocate, the number of replicates of each treatment, but in general I don't think it does. Now, the reason for not using the correct DS criterion is because it would not allow randomization, and it's not robust to the covariate model being wrong. So, although from the way I look at it, it looks like the wrong DS criterion, actually it's not that bad. And the reason it's not that bad, I think, is because optimality, D-optimality, DS optimality is somewhat related to orthogonality. So trying to choose the covariate values to be nearly orthogonal to the treatments is not that much different from choosing the treatment allocation to be nearly orthogonal to the covariate values. So actually it seems to work quite well, and I think that's why theorem 4.2 works. Just in my last minute or two, blocking. So in the present, I didn't see it in the paper, but in the presentation Jose mentioned that there were so many covariates, you'd have so many blocking variables that you'd have multi-way blocking. But you don't have to do blocking that way. And we tend to think of blocking, teach blocking, that given these blocks, this is how you choose a design. But actually the art of choosing blocks is something that is really important and perhaps really underexplored. How should we go about choosing blocks? Well, I mean, clearly we want to block units which are expected to give similar responses. So one complicated way you could use a prior model under some baseline treatment, and then your first 13, the 13 with the biggest prior responses are your block 1, and so on. Or perhaps we could use some kind of clustering. There are various sort of extensions of k-means clustering for continuous and categorical responses. But I wondered if some version of SCOMARS which avoids this flipping, forces the first two to be at the same side of the mean might work. I don't know. And then just to add what I was saying about design versus model-based inference, blocking doesn't preclude the use of models with continuous covariates, especially with the extended block designs. Although, if you've chosen your blocks well, they might not add much. So some of the things I don't have time to talk about, but I would if I had time. Treatment structure, there seems to be some structure among the 13 treatments. Interesting cases could arise where some treatment factors can be applied to families and some can be applied to individuals and some can only be applied to families, leading to multi-stratum designs. And in some of the further examples, I think, maybe the Moroccan microfinance one, we might question the stable unit treatment value assumption. It could be the treatments applied to some experimental units could actually affect other experimental units as well. So I think I've used up my time. So I'd like to thank the authors again for an interesting, thought-provoking paper, and it gives me great pleasure to propose the vote of thanks.
Thank you very much, Stephen. I would like now to call the second proposer, Simon Dave, who is the Director of the Clinical Trials Consulting and Training Limited.
Good afternoon, thank you. Well, firstly, I thank the authors and indeed the editor, reviewers and discussion meetings committee for bringing the paper for publication and some interesting discussion. I also acknowledge the passing of Carl Morris and during the period between submission and finalisation of the paper, and offer condolences to the co-authors. To simplify things down, the paper discusses an approach to randomising many units, people or some other defined unit, to many treatments, policy interventions, medical treatments and so on, whilst balancing for many covariates. My experience with randomised trials is almost entirely restricted to medical interventions, whether that's products, vaccines, devices, although with a bit of exposure to educational and policy interventions and a few of the ubiquitous agricultural trials too. So perhaps my scope of randomised trials is somewhat limited, leading me to say I find the methods and possibilities that you propose to balance so much across so many interventions as extremely impressive. But and my but relates to how useful is this? By far the majority of trials I have seen do not have large pools of experimental units, I call them people, waiting to be called forward. There are exceptions. Cluster randomised trials typically have all of the eligible clusters, villages, schools, whatever, known at the outset of the trial. Not always, but typically. And so-called bioequivalence studies seeking to compare pharmacokinetic properties of different formulations are typically carried out on healthy volunteers where we have a room full of hopefuls sitting and waiting to be called forward. But these exceptions aside, it does not generally seem practical to use a method that requires all possible experimental units that are to be randomised to be identified before beginning the experiment. I note, it was in section 8.3, but you picked it up in one of your slides, you talk about sequential experiments, by which you mean trials that randomise one cohort of units and then a further cohort and so on. But most trials just typically find the next unit, patient in my experience, and allocate them as a single unit. And then the next one arrives. Sequential trial is a term much more commonly used to describe a trial where accumulating data are repeatedly analysed until some threshold for statistical significance is met, It's not usually a term describing sequential arrival of patients, which almost always is the natural course of events. My next but is that the majority of trials I have seen have compared two groups. Some have compared three, and sometimes a few more, but very rarely more than that. I have seen so-called randomized trials where several doses of a treatment are being compared, but quite often those are compare dose 1 with control, and if there's no safety problems, then move on to compare dose 2 with control, and so on. So actually each patient is only in a two groups randomized trial. Now, there are exceptions to that, but that's mostly what I see. On this point of multiple treatment groups, the author's table 5 shows 10 examples. But most of these actually compare two groups. This column here. 2 of them have got 3 groups, 1 has got 4 groups. So it's not really the many groups scenario that the authors set out to address. Table 5 also suggests the authors of the case studies were trying to balance for a great many covariates, the column K here, up to 34 covariates in one case. But were they actually trying to do that? The authors of the paper certainly present a table of baseline characteristics showing how their trial did or did not balance across the treatments. But that's simply a reporting issue. There's nothing to suggest the authors had clear intentions to take a proactive step to balance all of those covariates. One example that I found particularly interesting, it was a very medical one, the one by Durosha. It interested me. They had 480 patients and allocated them to 2 treatments. And they did not use any sort of stratification or balancing technique at all, nor any covariate adjusted analysis. They seemed quite content just to let complete randomization solve the problem for them, as indeed it reasonably well did. And they present this table 1, and every clinical trial paper I look at has a table 1 in it that simply reports this is what we got. That's not the same thing as saying I'm actively, desperately trying to balance for these factors. Well, new methods and approaches are always to be welcome to discuss and consider their place, but, sorry, that word again, but what about asking how they compare with existing methods? The comparison in the paper seems largely against how a completely randomized design performs in terms of balancing. But could the authors comment on how their approach performs compared to other fairly simple covariate adaptive randomization procedures, such as the minimization procedure by Pocock and Simon or Taves from the early 70s? Minimization seems just as intuitive as the present methods, at least to me, and a whole lot simpler to implement. And I would just caution at this point, I've seen several instances of errors in computer programs used to implement even relatively simple minimization. Even in some very high-profile trials, one particularly, one of the ISIS trials of 27,000 or so cardiovascular patients. And although not in that case, but in some, these errors have actually sometimes completely invalidated trials. So implementing methods that are more and more complex does worry me somewhat, unless there really is some very good reason to do so. In terms of comparisons to other methods, the authors take a very similar approach to Atkinson in his Biometrica paper from 1982. He also used D-optimality, but noted that minimizing the generalized variance of the parameter estimates is not really what we're interested in a clinical trial. More specifically, we're interested in the variance of the treatment contrast. Other covariate parameters are really just nuisance parameters. So this led Atkinson to use so-called D-optimality that I think had been introduced originally in the early 70s by Simpson. So that's really to focus on the precision of the treatment contrast, not worrying about the precision of the covariates. And in this regard, I prefer Atkinson's approach to that of the current authors. But I do accept that if all the experimental units are identified before randomization takes place, then Atkinson's approach doesn't take advantage of that, whereas yours does. The author's proposal and other methods like minimization can handle large numbers of covariates, but again, it's not obvious that this is always a wise approach. Balancing for x1 and x2, because we know they are important, certainly is wise. But balancing for x3, 4, 5, and 6, and so on, just in case they are important, may not be. When there's multiple covariates in the pool to be balanced, there's inevitably some degree of compromise amongst the entire set of covariates. And I think naive researchers might think they're doing the right thing by including lots of so-called just-in-case covariates. But the consequence might be that the really important ones do not get balanced as well as they might have been, had they been the only ones in the pool. So I worry about methods like those we're discussing that too easily allow the trialist to include too many covariates in the balancing algorithm. And rarely have I seen the need to balance for more than 2 or 3 important covariates. And if that's all you need to do, then simple stratification might be adequate. In terms of being able to balance for lots and lots of covariants, I just warn, be careful what you wish for. So anyway, despite my reservations, I am pleased to see additional options added to our armoury of methods to conduct trials that can lead to clear answers to important questions. And so it gives me pleasure indeed to second the vote of thanks. Thank you very much.
Thank you, Simon, and I would like to thank all the presenters today for their excellent and insightful tasks. As per tradition, let's mark our appreciation by applauding. So now it's the time when we'll move on to the open discussion session. We have 2 people who have booked to comment, but after their presentations, we will open the floor to comments from both in-person attendees and online attendees. So if you are here in the Hallam Center, please raise your hand and come up to the lectern when called. If you're online, please use the raise hand icon or use the chat box. All comments, as I said before, can be written up afterwards and submitted by 19th November for publication with the paper in the journal. So we start with those that have given their names already. And I would like to call Joseph Newhouse from Harvard University, who is online.
Thank you very much. And thank you to the organizers for inviting me to comment on this paper. I should say that I'm an economist amidst statisticians, so you'll forgive me for not knowing the experimental design literature as well as you, but I'd like to start by observing that there are times when the gains from using the FSM will be negligible, and I give the example of Google randomizing different colors in its advertisements to see what generates the most clicks. So if you can get huge samples at a negligible cost, you can just use complete randomization. This, of course, is not usually the case in either clinical trials or public policy experiments of the kind that we had with the RAND insurance experiment. Oops, I gotta stop. Okay, so this was, as Jose said, originally developed by Carl, and Ambarish gave the example of the captains choosing teams on a playground. Now, the FSM, from my point of view, was underappreciated for a long time. possibly because Carl published it in an econometrics journal. I looked at Google Scholar. In the first 20 years, it was cited less than 10 times, not counting papers from the RAND team that were describing results from the health insurance experiment. It was cited a bit more after that, mainly after Don Rubin published his rerandomization papers. And I hope the publication in the JRSS Series A will end this underappreciation or seeming not knowing about the FSM. I gotta stop doing that. Okay, so Jose, Carl, and Ambrish improved on the original FSM as Ambrish described. I won't dwell on this. And they show that the gains are substantial if heterogeneous treatment effects are of interest. That was certainly the case in the RAND experiment, where we were interested in whether low-income households responded differently to insurance than higher-income households. I'm going to give a little historical context for where this came from. Ambrish described my first bullet. The government office that sponsored this experiment had begun analogous experiments in income maintenance, and two econometricians who worked on those experiments and developed a novel assignment method. I should say that I was the principal investigator for the RAND experiment. So these were John Conlisk, who was at UC San Diego, and Harold Watts, who was at Wisconsin. And their method was probably natural for two economists. They wanted to maximize an objective function subject to a budget constraint, and their optimization used something that was very similar to an optimal selection function. I'm sorry, am I muted? Can you hear me? Okay. And the problem with this method,
Joseph, hello there. Sorry, it's the technician here. We are showing your slides from this end. If you could say next slide for us, and then we'll advance the slide. We're on slide 3 at the moment.
Oh, all right. So I'm describing the slides I'm seeing, and you're not seeing that. So go back to slide 3 then. Oh, slide 3 is that this?
We are on slide 3 at the moment. We're sharing
that is
slide 3.
The finite selection model?
It is indeed, yes.
Okay, could you go to the next slide?
Yes, done that now for you.
So I'm not seeing the next slide, but
I think you're looking at your slide deck. If you go back into Teams, and then you'll see your slides.
That's all right. I have few enough slides that I can deal with that. So the FSM, as I said in this slide now repeats, it was not appreciated for a long time. And I'm hoping this paper will do something about that. You go on to the next slide. Jose described how the improvements on the original FSM that this paper introduces, and I won't dwell on that. And he also, if you go on to the next slide, he describes the gains when heterogeneous treatment effects are of interest. This was true. I got to the income maintenance experiments a bit later, so I'll go back to that example. That those experiments were trying to give households a guaranteed income if they had zero income, they got the guarantee. If they had earnings, the guarantee was taxed away at a rate until it got to zero. And the treatment effects that they were interested in were the varying the size of the guarantee and varying the tax rate at which it went to zero. And of course, the cost of the experiment varied with the treatment because obviously it was greater if households had a greater guaranteed income, and also if the tax rate was lower, which is where I got to. Could you go on to the next slide? Now, so the government, are we on now? The government urged us to use this method. Well, we didn't, because the minimizing the variances of the main effects subject to a budget constraint, in effect, allocated fewer high-income households to generous treatments so the designers could get a higher sample. That obviously impaired the ability to estimate treatment by income interactions, which was a key objective of both theirs and the RAND experiment. I don't think they realized that it was going to do this. So we did not use that. And in principle, of course, this could be addressed if, could you go on to the next slide? If you included in a model explicit functional form for the income interaction or any other interactions you were interested in, but theory didn't give us that functional form, and we did not include it. We did balance on many covariates, but we weighted those covariates. So for example, we gave, in the RAND experiment case, we gave the highest weight to prior year physician visits, which we knew, and self-rated health status at baseline. We gave very little weight to some other variables that we were interested in, but wanted to achieve some balance on. So if you go to my last slide to summarize, the original FSM was a substantial improvement, we thought, over the original methods. Carl Morris later calculated that we got a 25% reduction in standard errors relative to complete randomization. And Jose and Ambarish and Carl have not only improved on this with this paper, but they've provided an open source program in R to implement it with very fast runtime. So I'm hoping that this will become a tool in the experimental design kit. And thank you very much for inviting me and allowing an economist to intrude into the Royal Statistical Society.
Thank you very much, Joe. I would like now to call Hang Ding from the University of California, Berkeley, who is also online.
Hello, everybody. It's my pleasure to be here to discuss the wonderful paper by Jatabat and Jose and Morris from UC Berkeley Statistics. Next. First, I want to give an overview of my discussion. First, I want to congratulate the authors on an insightful paper on the finite selection model, SFM, proposed by Carl Morris in the 70s. Second, I will offer some more detailed comments, including my personal experience with FSM, quick summary of the paper, and some further theoretical directions for FSM, motivated by the theory of rerandomization I have been working on. for a few years. Yeah. Could you please go to the next one? Yeah, first, my personal experience with FSM. While I was a first-year PhD student, in the first semester, I took Dan Rubin's class, matched sampling and study design. And in the middle, of the semester, there was a group of students presenting Morris Journal of Econometrics paper on finite selection model. And Carl was in the audience to provide the background of the experiment and also the intuition he had. I think his intuition usually from sports, because he was a fan of it. And at that time, students did a lot of simulation study to compare FSM with classic experimental design, and they reported advantages of this design, but I don't think they went further to pursue any theory on this topic. So it's very interesting to see this paper continue this line of work. Could you please go to the next one? Here are some important results I took from this paper. First, they reported empirical evidence of covariate balance under FSM compared with complete randomization and re-randomization in their figure 1. They also made connections between FSM and the randomized block design and the matched pair design in their theorem 4.2. They also provide some inferential results under FSM in section 5. That's from a theoretical perspective. I found those results are the progress in the literature. Okay, could you please go to the next one? Because of my experience on re-randomization, I want to summarize what has been done in the re-randomization literature, and I hope and I expect maybe the parallel research can be done for FSM too. For example, these are the important topics we have been working on. A lot of other people also worked on for the past 15 years on re-randomization. Here are the results we can formally establish. Like re-randomization just means when you draw treatment allocation, you only accept the allocation when the covariates are balanced. Otherwise, you just keep on drawing the treatment allocation. It's like rejective sampling. Okay, the literature has documented the following results. For example, there is a formal theory about improving covariate balance compared with a complete randomization. That's a mathematical fact. But this is only the first step, actually, because covariate balance is not the final goal. The final goal is the treatment effect estimation. So covariate balance is like an intuitive goal. But this intuitive goal, if it's achieved, then it can ensure more efficient estimate, at least under re-randomization. The second point, the theory of re-randomization is relatively complete after the Rubin and Morgan paper. And the literature has already documented very detailed asymptotic theory, asymptotic distribution, how do we do variance estimation, how do we construct large sample confidence interval. It's a relatively complete package now. And more importantly, as Fisher was arguing, if you do experimental design, ideally your analysis should be simple, because otherwise what's the point of experimental design? From the current theory of re-randomization, we can run it, then run simple least squares. If you use the Eicher-Huber-White robust standard error, it also works under the design-based framework without assuming the model is correct. That's an attractive feature of re-randomization, because analysis is actually simple. You don't need to change anything, just the current practice of analysis. This part is a little unclear for other design, because for other designs, sometimes you need to change this and that, change regression formulation, change the standard error estimation. Moreover, recently we also established the following results in response to the critiques from some people. They were saying, oh, cool, you can do re-randomization, but you can also run complete randomization without doing anything in the design stage. As long as you do covariate adjustment properly, then the efficiency gain is ensured too. So the efficiency gain from regression adjustment and the re-randomization are actually the same. So if you do regression adjustment, the value of re-randomization is a little unclear, at least under the criteria of efficiency. Okay, that's not, so when we work on that, a lot of people push back saying this does not really see the advantage of re-randomization. So the new series is more than asymptotic efficiency. Re-randomization can reduce p-hacking. For example, even if you are in randomized trial, you can run regression adjustment. You can use different sets of covariates, and then can give you different estimates, slightly different estimates. If you adversarially choose, or if you strategically choose covariates to minimize the p-value and always report the significant one, then that's p-hacking, right? Then p-hacking, the hacked p-value does not have theoretical guarantee. But we show if you run re-randomization in the design state, you don't have that much freedom to do p-hacking, or even if you p-hack eventually does not hurt that much because the design ensures balance already. Then p-hacking cannot move the point estimates and stand the error significantly. Okay, that's we view it as a real benefit of the design, because in practice data analysis can be very complicated. We don't know how people analyze the data. We don't know how they report the results. So this part cannot be guaranteed by complete randomization, although efficiency can be achieved by fancier analysis. Okay, and final point, re-randomization can be extended to many other design, including stratified, factorial, and cluster design. This is my summary of the literature. So next. So what can we, next? This is, I have 6 slides, but that's page 5. Yeah, this one. Yeah. Okay. How about FSM? There were a lot of empirical evidence for covariate balance, but still, I feel we need to see is proved formally. And the paper also provides some unbiased estimation and calculates the variance of the simple moment estimator. But still, we want to see the full large sample theory for inference. And the third point is a model-based inference. Why do we care about model-based inference if we have experimental design similar to the least square strategy? Like we run least squares. Initially, it's motivated by a model, but really we don't really believe that model. Still, it works under the design-based framework. So I'm wondering, what is model-based analysis under this FSM? Having guarantees from both sides. If the model is correct, fine. If the model is incorrect, the design also ensures it's correct. And the fourth point, I conjecture that FSM can also improve coherence across estimators, so it can mitigate p-hacking. How do we formalize it? Conceptually, the FSM seems natural for various design, and I'm pretty sure someone can work on the extensions to other designs. My conclusion is it seems a lot of work can be done in the future. Yeah, thank you very much.
Thank you, Pang. I would now like to call David Firth from the University of Warwick.
This is an excellent paper. I thank the authors for presenting it here. It revisits some important methodology developed decades ago. I have two questions that occurred to me when reading the paper. There are lots of good insights here, and the main methodological development is the use of D-optimality as a selection, as an optimality criterion. This seems to have clear appeal where there's a linear model which works well for the relationship between the outcomes and the covariates. But what about situations where only a non-linear model will be satisfactory? And I have in mind here something like a fairly common situation, like the outcome being binary, for example, where we might naturally consider logistic regression rather than linear. In such a case, that the information matrix will depend on the unknown parameter values, and then natural approaches to optimal design are either Bayesian or sequential. The resulting designs that come from those Bayesian or sequential methods tend to be very different from the sort of space-spanning behavior that you get from D-optimality in linear models. And I just wondered whether the authors have already considered such problems. That was my first question. The second question came up actually during the presentation by Ambarish. There was this beautiful explanation about picking teams in the school playground. And well, so I'm dredging up my memory of the school playground here, but the best method that we, in the end, always used was to flip a coin once to pick to see which captain would pick first, and then you'd take it in turns to take the first. So you pick for team one, then team two, then team one, team two, team two, and so on. So you'd alternate in a purposive way rather than randomizing at each selection. And I would just like, if possible, for the authors in their rejoinder to clarify why it's better to randomize at each stage rather than randomize in that more coarse way at the beginning, perhaps. So that's my second question. And I'd like to just end on a more personal note. Carl Morris and I were colleagues at UT Austin in the late 1980s, and we've been friends, we were friends ever since. It's even though it comes, unfortunately, after his death, it's wonderful to see this further development of Carl's influential earlier work. And I thank the authors again for doing that. Thank you.
Thank you very much, David. I would now like to call Rosemary Bailey from the University of St. Andrews.
Thank you. So I'll join everyone else in saying thank you to the presenters for that interesting talk. But I do have a few comments. Gosh, if I can read them. Something that you said several times is that re-randomization is commonly used today. Now, I don't think that's totally true. My work is mostly in agriculture or ecology, or sometimes in things to do with medicine. And re-randomization is simply not allowed because that causes you to cheat if you don't like the outcomes. So you have to think in advance, what is my block structure, what do I think will matter, and randomize accordingly. And there's even this notion called restricted randomization, at least we call it restricted randomization, Americans call it constrained randomization, where you can say, okay, something like, if we start with this design and only use a two transitive permutation group, not the whole symmetric group, then we have validity in our analysis, but we ban certain bad patterns. So that's the thing to think about. Re-randomization is not universal, and it can have bad effects. It can cause bias. The other main thing that I found really strange was, again, I think Steve probably mentioned this. In your example, whether you had that table, you go along in pairs and you put treatment 1 on one and treatment 2 on the other. And the way you do that, you start off and say one treatment chooses the most extreme thing for them, and then the other one chooses the most extreme thing for them. But given that that other one's already been chosen, very often you end up with choosing the two opposite extremes. So although most of these, what I'd call blocks, might be similar on average, they're not similar in the sense that blocks usually are. And normally what you would do is try and make things as equal as possible on all the relevant covariates and call that a block. And not only that, having used the blocks in the design, you would also use them in the analysis. That's one of the, I would say, standard rules of how you go about things. Well, if there's stuff that I can't read because of the light, I'll put it in the written one. But I just wanted a thing that I was just a bit puzzled by. At the beginning of section 4, you introduced this bold beta. And I don't think you ever say what it is. So if you could explain that, that would be helpful. I'm sorry, I'm a pedant. I like things to be explained precisely. Anyway, thank you again.
Thank you, Rosemary. So now we'll move on to the open discussion session. Sorry, wrong sentence. So I now invite contributions from the floor. So from those ones that didn't give me their name, is there anyone that would like to contribute to the session? No, how about online? Do we have anyone online that would like to contribute to the session? No? So in that case, I think we can now give the opportunity to the authors if they want to reply. You don't have to, but do you want to? Okay, so you have 10 minutes.
Thank you so much, Professor Gilmore. Thank you so much, Professor Day, Professors Newhouse and Ding online, and Professors Firth and Bailey here for your insightful comments. I'm going to provide a bit of an overview of the comments and a quick reaction to then allow Ambaris to go deeper into subjects if you want to. We haven't practiced this. So Professor Gilmore raises the relevant question of the connection of what we're doing to the very deep and formal literature of design of experiments. I think that's a great point, a great direction that we ought to explore further. In particular, I thought it was very interesting, this idea, this notion of the art of choosing blocks coming from the matching literature in observational studies. We observe this course of dimensionality. You can exact match or block for so many things. If you have 20 binary covariates, there are 2 to the 20 type of blocks. If you have 30, as my advisor says, there are no humans on Earth to exact match on everything. So there's an art in that. I agree with that. And your idea of using the prior model under a baseline treatment, I think, is very insightful, connected to what we call the prognostic score in observational studies, so that I think it's a very interesting direction. Any comments in this regard? Professor Day looks at the paper from the standpoint of medical science, randomized trials, and he kindly but clearly raises like 3 buts, okay? And I think he's right. He takes this practical standpoint. First of all, he says, most of the experiments we have in medical science are sequential. People arrive little by little to the hospital. I think that our reply here, because we have thought about this with Ambaris and Carl, is that it is true. If batches don't get to accumulate, the FSM will not do better, but it's not going to do worse. But as soon as you get to accumulate a bit of patients, this design does better in terms of the metrics that we described at complete randomization. But that's a fair point. In other settings, for example, when we're randomizing villages and so on, like in some of the examples we mentioned, that tends to happen. I mean, we have all the units before. You made this observation about that in our 10 experiments, we didn't have many treatments. That's true. It was very hard for us to find them. This was motivated by the HIE. But in the tech industry, I do think we have these kind of things, and it's good to have a tool that can target this. Thank you for mentioning the work by Atkinson. I don't know that paper, and I have to take a look at it. Maybe you know it? No? All right. So then the third comment had to do with the selection of covariates to balance. Critical question. A question that I would react to citing Fisher, being in the UK. Okay, I think he said, and here I'm drawing again from my advisor, Paul Rosenbaum, Fisher would say, make your theories elaborate. So before running your experiment, before designing your observational study, think. Think about what you know, okay? And try to design the experiment in a way that is deeply connected to the science, the substance knowledge. And that is going, hopefully, to motivate using some covariates more than others. The FSM provides a tool to emphasize those covariates. Personally, I think it's better to have the tool than to not have it, rather than doing uniformly okay on everything. To me, the big point of the paper, if I were to emphasize one message of the paper, citing Ambarish here, is this idea of how vast is the space of possible treatment assignments, and that we often leave money on the table when we just randomize. Again, citing Paul Rosenbaum, we want to give randomization a push from optimization. The FSM is doing this in a greedy way. Greedy in a strictly technical way. It's not fully optimizing all the way through. And it's doing that to introduce randomness at each stage. But the point is that the space of possible random assignment is so vast that even when we give full advantage to re-randomization, the worst case of the FSM does better in terms of balance. So that's that. Then minimization. This is connected to using mixed integer programming and so on. The point is, again, citing Fisher, using randomization as the basis for inference. To my knowledge, minimization, in terms of the original proposal, doesn't have randomness, I think, to justify inference. Yeah, good so far. Okay, then Professor Newhouse provided some very valuable policy context. I very much welcome an economist in this conversation. And he made the HIE happen. Decades later, we're still citing the results from that experiment to do policy in the US, and the FSM was invented along the way. Thank you, Joe. Thank you for mentioning the FSM to us and to work on this so that it's more appreciated. Professor Ding always blows my mind with his comments. And he emphasized the methodological side. And in the last slide, he offered directions for future research. I think that Professor Chattopadhyay is already working on some of them. Any reactions?
Yeah, I think this is very interesting. Like, there are very
You
many
need to come
parallels.
closer.
No, nothing really significant to add. There are many parallels to the way the trajectory of re-randomization theory and with the FSM theory. So there is definitely scope of working on these areas. So thank you, Professor Ding, for mentioning that.
Professor David Firth, thank you so much. He mentioned other models, other criteria. I think he, in a very key manner, used this term of space-spanning behavior. And that motivates a lot of our thinking. We tend to think about this in terms of like basis functions that span a function space for an unknown outcome model. The question is what to emphasize in connection to your question. Why is it better to randomize at every stage as opposed to only the beginning? That's a fuzzy question to me. I think it's a great question, but it's a cloudy question in my mind because how much randomness there ought to be?
Again, like we keep referring to Fisher for every question. So if you do it for every pair, you increase the space of randomization. If you're doing it at the very beginning, there are just two options, 1 to 1 to 1 to 1 to, or 2 1 to 1 to 1 to 1. So it doesn't provide enough randomization to do randomization based inference. That's why we do the blocking thing, the pairing thing.
And Professor Rosemary Bailey, it's an honor to meet you in person. Thank you. Your comments came from agriculture, medicine. I wish I knew more about the domain of agriculture. We will clarify what bold beta is. Sorry about that. I just wish to clarify something that I think we mentioned briefly. If we only give indicators for the blocks, we retrieve a block design.
Yes.
Mm-hmm. But you're right that with continuous covariates under D-optimality, D-optimality is trying very hard to cover the range of the covariates to minimize the standard error, so to speak. And because it's doing it in both arms at the same time, they're kind of like being representative of each other. But you're right that there's a trade-off there. Thank you.
Nothing much to add. It's just that we are looking at the balance at the end of the assignment. So after the first two changes, as you mentioned, I choose a very old person, and the next guy chooses a very young person. But after the next two, it gets balanced back again, right? So at the end, it all balances up.
Thank you.
Thank you so much.
Thank you very much, Jose and Ambresh. So you can, if you wish, then to write a more considered reply to these questions and any questions that people will submit by the 19th of November. Okay. So if you're wondering when the next discussion meeting will be, full details of all the upcoming meetings are available on the RSS website, and they are also announced in the members' newsletters and on social media. If you would like to receive an invitation for future discussion meetings, please email journal@rss.org.uk and we'll add you to our discussed mailing list. And that is it for today. Thank you very much to all that contributed, and especially to the main authors. We do have now a reception downstairs in the Wigmore suite, and you are all welcome to come along. So if you just follow a member of staff downstairs, or you can of course just take the lift. Okay, so that's all for today. Thank you very much for coming.